Hi there, welcome back to this channel. In this video, we are going to be talking about waves. Now, this is going to be the first video in the series of wave videos that we're going to make. And here we're going to be capturing, in this video, we're going to be capturing the definition of wave, the types of waves, the classification of waves, and then the terminologies used to describe a wave, and then maybe even the characteristics of a wave motion. Now, what is a wave? Now, a wave is defined as a disturbance. So first, know that a wave is a disturbance. So a disturbance that is made at a point and therefore transfers energy from that point to another point, but without the actual displacement of the molecules or without the actual apparent displacement of the molecules that are carrying the waves of the substance in which the disturbance is happening. I'm going to repeat that. I said that a wave is basically a disturbance or a vibration that is made from a source. So, and from that source, it transfers energy to another source, or it is transferred to another source, carrying energy with it. Is that okay? So, but without the actual displacement of the molecules of that body that on which that wave is being transmitted. Is that okay? So what you notice is that a wave transfers energy from one source to another, but without carrying the atoms of that substance on which of that material on which the wave is happening on. Is that okay? So it is not carrying the atoms of that material, but energy is being transferred from one point to another as a result of that wave. So it is primarily a disturbance. Now, what are the classifications of waves? Now, we have two broad classifications of wave. We have a progressive wave and we have wave that is stationary. So let's talk about the classification. So we said it is a disturbance that transfers energy. So let's just put that there. It transfers energy from one point to another without apparent displacement of the material. All right. So we said the classifications. So in the classifications, we have first two broad classifications of waves. The first one is the progressive wave. So what is a progressive wave? You say something is progressive. You say something is progressive, what does it mean? It means the thing is moving. Is that okay? So we say a moving wave or a progressive wave, a wave that is not stopping. Is that okay? A wave that ideally is just continuing. Is that okay? So that's a progressive wave. And then we have one that is stationary. Stationary. So nary, that is not nary. You know, the other one is the E, which is referring to your writing materials. This one means static. Static at a point. Is that okay? So stationary or static waves. All right. So now, then the progressive waves are further grouped now into two, which are the mechanical waves, and the EM waves, the electromagnetic waves, or you just see EM waves, EM for short. All right, electromagnetic waves. Now, I'm going to still explain all of this, but let me just break down the classification. Then we can now have the mechanical wave is also further divided into longitudinal or transverse. So we have longitudinal or transverse wave, and while the other one is this is where I'm going to also write it. The mechanical wave is split into longitudinal or transverse wave, while this guy is primarily transverse, all transverse. I mean, EM waves are not longitudinal, but mechanical could be longitudinal or transverse, while electromagnetic waves are almost always transverse. So let's talk about a progressive wave. What is a progressive wave? I said is one that is continuous. Is that okay? So you will see it being represented in this way. This is the typical diagram of a wave, a progressive wave. Is that okay? Of a wave motion. So this is a typical diagram. So this is the one that we use for the progressive wave. And why is it called the progressive wave? In fact, if you look at it, you see it's a continuum. Is that okay? So it's a continuum. So that is why it's called a progressive wave. And then a stationary wave is one that happens within maybe closed tubes or between 2 points. So, for example, if I tie a rope onto a, excuse me. So if I tie a rope onto 2 poles, now the wave, and I create a wave to travel from one point. So if I tie 2 ropes here, tie a rope here, and then I create a loop here, that wave is going to travel here and back and forth and back and forth, and it's going to create what is a stationary wave. Is that okay? So that's what we'll call a stationary wave. Now, both waves have their peculiarities, and that's why we fundamentally group them into those two broad categories. Now, what is a mechanical wave under the progressive wave? Now, a mechanical wave is one mechanical wave. So let me write that here. Mechanical wave are the ones that require material mediums for propagation. So they require material media for propagation. So for example, a sound wave is a mechanical wave. Another example is the water wave. So that is indeed a mechanical wave because it requires water to actually exist. Sound requires air to actually move, to actually, for you to hear sound, air must be present. In fact, one of the experiments carried out, I think by Eugene or one of those scientists, I think Eugene, was to use a bell jar to validate the fact that sound required air for transmission. So without air, sound would not be heard. So an air is a material. Air is a material. So one of the times when I was talking about concrete nouns, I talked about air. I was telling some of my students, and I said air is actually a concrete noun. So some of them were, but we can't see air and the rest of that. But air is actually a property. So I made them know that, in fact, air is matter because it occupies space. So, for example, where I am right now, air is not in the exact position. Once I leave there, then air can diffuse into the place. Is that okay? So, that is not to say that air cannot permeate a thing. But, for example, this board is in this place, and so in this place where this board is, there is no air. Maybe just in front there is air, and just at the back there is air. But when I remove it, then air can now enter that space. That's just to show you the material nature of air. Is that okay? So, sorry for the digression. It was just to show you that air is actually a material medium, so that air would be needed to be present for sound to be heard. So that validates the fact that that a sound wave is indeed a mechanical wave. And of course, water wave, it needs water to be available for water wave to be produced. So that is why we see water wave on the ocean. So it rolls to the shore and back into the water. So that wave needs water to actually be produced. And of course, the ripple tank, if you drop a stone, for example, or you just take a drop of water and put it down, drop it back, or take a make a droplet of water, whatever, just drop water into a bucket containing water, you're going to see ripples beginning to spread. So that is a wave. So it required water to actually happen. So that's a mechanical wave, requiring material medium, without which they will not be possible. Those waves will be impossible without material medium. And then, coming to the electromagnetic waves. The electromagnetic waves, or the EM waves, or the EM waves, are the waves that are created when you see the word electromagnetic, electro referring to electricity, and magnetic, referring to what? Magnetism. So, and you know the Earth has a magnetic property and an electrical property. So, the magnetic field of the Earth and the electric field of the Earth do interact at 90 degrees, interact perpendicularly to each other to create these waves. It's a spectrum, in fact, so there are a lot of waves that are created. Not like it's actually a spectrum, okay? So, and within that spectrum, we have different types of waves that are created because of what? The Earth's magnetic field and the electric field interacting at 90 degrees. So, and that is why it is possible for them to be transverse. That's why it is possible for them to be transverse. We'll still get to this. We'll still get to this. All right, but so you are seeing that these waves are being produced when two fields interact at 90 degrees. So that one is interacting at this angle, the other is interacting at this this plane, the other is interacting along this plane. So you're going to see something like this. It's usually best viewed in the 3D perspective, such that if I have the first one interacting this way, so if this is the first, if this is my electric field, my magnetic field is going to interact with this guy at a 90-degree angle. And how is that visualized? So something like this, think of something like this. I don't know if I drew that one. Let me redraw that. What I meant was this. So then you now see one that is interacting in this. So think of this wave, this other wave, as going into the board and coming out of the board. So this is wave B and this is wave A. So think of wave A as going into the board and coming out of the board. So that you have them at 90 degrees to each other. So on a 3D perspective, you're going to have something like this, and then maybe a marker is coming out of the board. So this is the other wave. So there are two planes on which both of them are interacting. So this one is interacting on X. So the first, if this were to be my electric field and this is my magnetic field, so my electric field is interacting at XY plane, then my magnetic field is interacting along the ZX plane. Is that okay? So there's going to be a ZX plane here. So this is my Z plane, or maybe even like this. Okay, let's just take it like this. So on my Z and X plane, my magnetic field is going to be interacting with the electric field. So this is the spectrum that is then produced when this occurs. I hope we understand what I'm talking about. When the electric field and magnetic field interact at 90 degrees to each other. So what the spectrum that is produced is called the EM spectrum, electromagnetic spectrum, and it is called the RMI Vox G. RMI Vox G. So R standing for, okay, let me write it this way, RMI Vox G. So R standing for radio wave, M standing for microwave, infrared wave, V standing for visible light. Okay, so I'm going to be explaining something about this wave. We're going to explain something. This one standing for ultraviolet. And you don't even need to memorize. You can just understand them and actually know what it is. But of course, this mnemonic should assist you in understanding it. All right. Gamma rays. All right. So we have this. Now, this order is in the order of their decreasing wavelength. So from here downward, we have wavelength is decreasing. I'm going to talk about this wavelength in a jiffy, but just know that this order is order of decreasing wavelength and order of increasing frequency. So this is the order of decreasing wavelength and order of increasing frequency. Is that okay? So they have nearly the same speed, but not all the same. Is that okay? They have nearly the same speed, but not all the same. And well, still going to talk about electromagnetic waves separately. But I just wanted to notice some things here. Now, in your textbook, you might see something like this being written or being drawn. You have a spectrum, RMI, Vox-Phi. So you have something like this being drawn. And then you now see a loop like this. Now, let's put it here. You now see a loop like this. Now, while this is here, and then you see something like this. So this is actually showing you, now this, all of this, from here to here, is showing you the wavelength. Is that okay? In your textbook, if you do see this kind of diagram. So, and this other place here is showing you that there is another spectrum here. And this spectrum belongs to the spectrum of visible light. So here, you're going to have the radio wave. It's going to have a larger wavelength. From here to here is bigger. Then microwave is going to have the next large wavelength. Then this one, infrared, is going to have that. And then ultraviolet is going to have the infrared ray is going to have a larger wavelength than the visible lights. Now, in the visible light spectrum, we also have another spectrum, and that spectrum is the Roy-Big spectrum. Roy-Big spectrum. And what's the Roy-Big spectrum? It's just the red, the orange, the yellow, green, blue, and indigo, and violet. Is that okay? You already know that from our basic rainbow colors. Now, also, please make sure you follow this series to the end, because I'm going to be talking about this visible light in another video about how color is, about color formulas, calculation of color, and those things. Is that okay? So make sure to just follow this series to the end. Now, you see these names are actually very, they are significant. So, for example, you are going to see just before, so this spectrum is also their order of increasing, this is their order of increasing wavelength. Is that okay? And the order of decreasing speed. Is that okay? This is the order of increasing wavelength and decreasing speed. The order of increasing wavelength and increasing speed. Yes, I think it's increasing speed. The order of increasing speed. Is that okay? So the order of increasing speed, since speed is direct proportional to wavelength, all right? So, but that is not even what is most important right now. But what I want you to see is this, that just before the red, we have infrared. Is that okay? Infrared is just in the visible light spectrum. Infrared is before the visible light spectrum where we have the red. So infrared means below. Okay, the word infra means below or sub. Is that okay? Sub, super. All right. So infra also means below. Super means above. The same way ultra means above or higher. Is that okay? So we have infrared waves and we have ultraviolet waves. So ultra means, so infrared means below red. Is that okay? And after the visible light, which is having the violet ray as the last, after that we have the ultraviolet. This is greater than the violet. Is that okay? So that is how to just memorize that. And so that is the reason why I said the names are actually significant. So that is a little bit about the EM wave. We're going to talk about their characteristics and their uses much later, but let's go over to the next. So what is a longitudinal wave? Now, we talked about the fact that the mechanical waves are divided into two, which are the longitudinal and the transverse wave. Now, the longitudinal waves are waves that travel in a direction that is parallel to they travel in the direction that is parallel to the motion that produces them. So if the motion that produces them is forward, they will travel forward. If it's downward, they will travel downward. An example is the sound wave. So a sound wave is a longitudinal wave because if, as I am speaking now, the ripples, okay, now, so this is going to be my mouth. This is going to be my mouth. Okay, I'm just trying to. So this is going to be my mouth, and as I am speaking, the waves are coming out this way. Do you understand? So the wave is traveling in the direction of the motion that is producing them. So the motion of the air is pushing against, so the vibration from my vocal cords, when they vibrate, my vocal cords will push air out, will push air that is closest to my mouth, and as that vibration pushes the air, that air pushes the next air, and I'm going to represent that. We are going to get to the representation. So that air pushes that, and that the next one, and then the other one pushes the next one, and that effect is being transferred that way. Do we understand? So that is a longitudinal motion. But a transverse motion, a transverse wave rather, is one that travels in a direction that is perpendicular to the direction of the motion that produces it. So if the motion that produces is going this way, the wave will travel in this direction. So for example, we could have water wave, for example. Like I talked about the ripple tank. If I throw a stone, if I take a stone and throw it into water, the motion of the stone when it gets into the water, so this is the stone as it's going, and then when it gets into the water, it goes down and then comes up. Do you understand? So what you're going to see is it goes down and up. Is that okay? So at this position here, this water here, so for example, let's say we are able to take just this particular water at this point. Is that okay? This water will come down and go up back. Well, it's going to be displaced, yes? So it's going to be displaced downward and upward. So by the displacement upward and downward, the motion that is producing is this upward and downward motion. But what you will see is a ripple being produced this way on the surface of the water. So the wave will travel this way, the ripple travels this direction, but actually what is happening is that this upward and downward motion is being transferred. So instantaneous, at an instantaneous position, at a particular position, at any particular position, at any given position, at any given instance also, what you will see is an upward and downward displacement of the surface of water at that point. But what you will see overall is a wave that is moving in both directions. Do we understand? So as the stone is dropping in water, you see a wave spread in the opposite direction. So that is a transverse wave. Why? Because the motion producing is going upward, is moving along the XY plane, along the Y plus Y and minus Y plane, but the wave is felt along the negative X and positive X axis. So that is a magnetic wave. And that is why that is a transverse wave. And that is why the EM wave is a transverse wave. We talked about the fact that it is produced when electric field and magnetic field interact at 90 degrees to each other. All right. So now, let's talk about what produces a wave. We've talked about the fact that it is vibrations essentially produce wave. So the wave is a disturbance. Is that okay? All right. It is due to a vibration, or sometimes it could be an oscillation. Remember, we talked about oscillatory motion. So, and we said this is what produces wave. Now, so if you had seen that video, if you have seen that, I'm going to link in the description, where we talked about oscillatory motion, starting with circular motion. We talked about the fact that oscillatory motion had a direct relationship with circular motion, and now we are talking about the fact that oscillations are what produce waves. So, and yeah, we can make sense of that. We can make sense of that. Let me show you something. For example, we talked about oscillatory motion or simple harmonic motion as one produced when maybe a spring, for example, if my hand were to be a spring, and a ball was to be tied to that string, for example. So let's say ball is tied to this spring and it is displaced. Let's say I drew it and it's elastic. Is that okay? And I drew it. So what you would notice is that this guy is going to be going up and down this way, isn't it? We talked about it's going to be going up and down, up and down. So now let's see Let me show you how that translates to a wave. So actually, because it is going up and down and is having in the rhythmic form, we call it a simple harmonic motion. You are going to see, if my body were to move, you are going to see how it looks like the progressive wave that we talked about. So since this thing is going up and down, then what if I were to move? So what did it produce? You see what? You see a wave. But my hand never stops moving up and down. My hand is still moving up and down. But what I'm going to produce afterwards is what? Is a wave. My hand is only moving up and down. Only my body moved. Is that okay? So it means that the motion of the simple harmonic motion is a very good example of what? Of a wave motion. In fact, it is synonymous to what? A wave motion. So oscillations, in essence, we say oscillation produce what? Produce a wave. Now, what are the characteristics of a wave? So first, let's examine what a progressive wave looks like and what a stationary wave looks like. So, if let's first talk about the stationary wave. A stationary wave, when our mouth produces that sound, what you're going to see, or a speaker produces a sound, what you're going to see is that the pressure is going to be sent to the air that is closest to the mouth or to that speaker. So when that pressure comes, it's going to compress the air closest to that mouth. At this point of compression here, the next layer of air is expansive, is not contracted, there's no pressure. Is that okay? Is diffuse. Is that okay? The next layer of air is diffuse. After a while, you see that this is going to send this pressure to this point, and this point becomes what? Pressurized again. So we call it compressed or compression. And then this one will become what? Diffuse. We call this point rarefaction. And this is going to transfer this wave to the next point. And then you have another compression. At that point, the front here is relaxed. Then that keeps going. That series of transferring of the pressure keeps going until you have points of what you call compressions. We call these points of compressions. And here you call them, so we call these 2 points compressions, or call these points of rarefactions. So why do we call them compression? Because you see that the pressure is higher there, so the wave motion, that energy is being transferred here. So you are going to see then why points of lower pressure are what? Are rarefactions. All right. So this is that of a sound wave, of a longitudinal wave. Not stationary. I'm sorry, I called it stationary. Of longitudinal wave. Now, how about a progressive wave? How about a progressive wave? What you're going to see is, now that thing is also typical of the stationary wave. If it were to be talking about wind instruments, waving wind instruments, is that okay? So, and this point is, now those points of rarefactions and compressions, they are synonymous to the points I'm going to be showing us on this wave, on this transverse, on this progressive wave. So what you're going to see is a diagram that looks like this. All right. Now, these points, all of these points are very important. All of the points here, they are very important. Do you understand? And they have their individual meanings. So with this, we are going to be talking about the terms or terminologies used in wave. So what are the terminologies? Now the first one I'm going to be considering is this point of maximum displacement and point of minimum, the 2 points of maximum displacement. This is the trough and this is called the crest. They are both points of maximum displacements. The point of minimum displacement is this. That is, there is in fact zero displacement. And you are going to notice also that there are the points where the wave is going to have the maximum speed when we were talking about a simple harmonic motion, where if the body, just follow me, you're going to get this, just follow me. And if you have not already, please do well to watch those videos that I posted on simple harmonic motion. I'm going to link them in the description. So if the body was at rest in this position, by the time it's where, by the time this body is disturbed, for example, if I draw it, the point of maximum displacement is going to be something like around here. So this is point of maximum displacement from this point. Is that okay? So this is x equals 0. This is 0 point. So this is going to be x 1 point. Now, by the time it returns, it's going to return to somewhere around here. So that point, so I can have something like this. So this point is going to be the point of negative x. Now, by the time this guy moves the farthest, its farthest is going to have come here. Its farthest, this place. But the point of highest speed is here. Why? Because this is the point of zero speed, this is the point of zero speed. This one is going to have highest speed here because this is the point from which it was what? It was going to begin what? Another displacement. Is that okay? So the same way here, this is the point where it's going to have the where it's going to have its this is the point of no displacement. So its speed is going to begin to increase from here. Its speed is going to increase from here. Do you understand? Its speed is going to increase from here, and it's going to be maximum at a point around here. Is that okay? It's going to maximum at a point around there. And this point is going to be a point of zero speed. Why? Because the body is going to stop momentarily. Mistress. Yes, ma'am. The body is going to stop momentarily here, and it's also so this is the point where it's going to be having its highest push. This is the point where the velocity begins to increase. Is that okay? The velocity increases and becomes, or decreases and becomes 0. The velocity actually increases and becomes 0, and then the velocity decreases here. Increases here. The velocity is 0 here. Is that okay? Because it's stopping momentarily. So, but as it is going here, it's going to increase and become maximum at a point here. Is that okay? And then reach here, become 0, and then go again. Do you understand? So it's going to become 0 here, 0 here, 0 here. You understand? The velocity is going to be 0 at those points momentarily, but at points here, around here, the you know, this is the displacement. So if we draw a slope of the graph, we're going to have a straight line which is going to be maximum at this point. Do you understand? So, and then 0 at this point. All right. So that is what we have for the crest and troughs. Okay, I was just talking about the speed and oil. And we are still going to get to that, but I just wanted us to understand what crest and trough is. So crest is the point of highest maximum displacement. Crest is the point of highest maximum displacement, and trough is also the highest maximum downward displacement. So crest is highest upward displacement, maximum upward displacement, while trough is maximum downward displacement. All right. So we represent them with positive and negative amplitudes. We're going to get to amplitude later, but this is not to say that those negative actually means minus, in fact, but it's just position based. So if it's upward, we say positive. If it's downward, it is what? Negative. Now, so that is crest and trough. Now let's talk about the amplitude. Now the amplitude, so the highest point here is crest, the lowest point is trough. Amplitude is also the distance, the maximum upward displacement in terms of distance now. So the highest upward or downward displacement is the amplitude. Now let me re-explain. The amplitude of the wave is how much farthest it can go, the farthest it can go upward or downward. But that point, this point is called crest. That point is called trough. This point is called crest. That point is called trough. But talking about where it can get to in terms of distance, So the distance from here to here is what you call amplitude. The distance from here to this point is what you call what? Amplitude. Do you now understand? So amplitude is denoted by A and is measured in meter. Do you understand? So it is going to be a vector. Is that okay? Versus what? A displacement. All right. So what did we say? We said that amplitude is the point of maximum upward and downward or downward displacement. Okay. Let's talk about the period of motion. So because it is synonymous to an oscillatory motion, then it's going to have what is called a period. So what is period? The period is going to be the time taken for it to complete one revolution. So first, what is one revolution? A revolution is basically a complete cycle. So let's talk about a revolution first. A revolution is what? A complete cycle. So what is a cycle? A cycle is a complete back and forth. A complete back and forth. Do we understand? So when it has come here and then returned again here. Do you understand? So this is a cycle. And in fact, you might see some, this is not ideally correct, but like it's a way of visualizing it. It's a way of visualizing it because we are not talking about circle here. It is different from, the word cycle is different from circle. So, but in fact, you can make sense of it. Cycle simply just means something that is happening repeatedly. Is that okay? Repeatedly. So it forms a cycle. So, but a way of visualizing this is it makes a circle. How? This top to this place, that's 180 degrees. Another here, 180 degrees. So you see, it makes a circle. So when you see a shape like this, it's going to be called a complete cycle. Is that okay? And in fact, so, but what we are talking about here is that a period is now the time taken to complete what? One revolution. So we say it is time. So we say period. In some textbook, depending on the convention, we use P or capital T. So we say it is that period is given by the time per number of revolution. Time per number of revs. Is that okay? The time taken per number of revolution. That is the period. Now, let's talk about what the frequency is. The frequency is just the opposite of what we had there. The frequency is given by F. Now, period is measured in seconds. Of course, you see time here. It's measured in seconds. So, frequency is the number of revolutions. It's just the opposite of this. Number of revolutions completed per time. Number of revolutions what? Completed per time. So that's why you have it was 1 over what? T. It's the same as what? The inverse. It is the inverse of period. It is the inverse of period. So that's why the unit is going to be what? Per seconds or hertz. Those are the two units that we use for frequency. So we say period is what? Time taken to complete one revolution, while the frequency is the number of revolutions completed per period. Is that okay? So it's just, that's why it is per period. So F is equal to 1 inverse of period. All right. So now let's talk about the wavelength. Wavelength is denoted by lambda, and it is defined as, for simply one cycle. A complete cycle is a wavelength. A complete cycle, a complete revolution, one rev, is what? Is a wavelength. So this is a wavelength. Now there are 3 definitions I'm going to give us for wavelength, and listen carefully. So we said first, it is a complete revolution. I said the revolution is like from here to here. So if I were to complete this, this is going to be, from here to here is going to be another revolution, another wavelength. So altogether here we have 2 wavelengths in this entire wave, from here to this point here. Let's name it A. To this point A, we have 2 wavelengths there. So that's the first definition. The second definition is a wavelength is the distance between 2 successive crests and 2 successive troughs. Using the layman explanation I gave the other time, think of this point as a quarter. In fact, it is a quarter of a cycle. because it is 90 degrees here. You see it? 90 degrees. So we have 90 degrees there. Here we have 180 degrees. So there we have 90 degrees. Here we have 180 degrees. And in the other end here, we also have another what? Another 90 degrees. So that's altogether what? 360 degrees. So does that make sense? Yes, it does make sense. So it tells you that what? A wavelength is also the distance between two successive crests or two successive troughs. So from here, from this point to this point is what? Is another wavelength. From this point to this point is a wavelength. So that is the second definition. The first one I said is a complete revolution, or you say the distance between two successive crests and two successive troughs, or in a standing wave. This is usually used in a standing wave motion. In a standing wave, we could say that a wavelength is the distance between three nodes or three antinodes. So what is a node first? A node is the point of minimum zero displacement. So these are the points of minimum or zero displacement. I hope this is not too rough already. So this is a node. This is going to be a node. This is going to be an antinode. This is going to be a node, sorry. No displacement. A node, a node. So if I have three nodes, that is a wavelength. So this is a wavelength. From here to here is a wavelength. You see, it follows what we already explained. Or three antinodes. 1, 2, 3. So antinodes are the points of maximum displacement. See, it corresponds with this point, isn't it? So this from here to here, which is the distance between what? Two successive crests, is what? Is our antinode. So what do you see? That a wavelength is basically what? A complete cycle. One complete revolution. All right, so that's that about our wavelengths. Now let's talk about the next terminology, which is going to be the velocity of a wave. The velocity of a wave. So what is velocity of a wave? Velocity of a wave is basically the distance covered per period. Is that okay? Distance covered per period. So, and it's also giving us the product of frequency times wavelength. So for example, what did we say about frequency? We are going to come back to the calculation. That's why I'm leaving them here. We're going to come back to their calculations. So we said it's given by frequency times wavelength. First, the wavelength is measured in meters. Is that okay? Wavelength is measured in meters. So that these guys, and we already said that this guy is measured in frequency, is measured in per seconds, right? So if this is measured in per seconds, and this is measured in meters, what does that give? Meters per seconds, which is the unit of what? Of velocity. So, and that makes sense. That makes sense. Why? Because frequency is how much revolution it is covering per time. How much? So that's just like how fast it is. Is that okay? Then times the distance that it covers. Do you understand? So that is the speed of the wave. That is the velocity of the wave. And we are using the word velocity here because it's a vector. Now, so let's now apply these ideas in context. Or let's talk about, we're going to talk about phase next. But let's apply these ideas using a particular wave motion. So let's say there was a wave like this. If we're given a question like this. And you were given this place to be 2 meters. And then this place is given to be -2. So you are asked to find the amplitude of this wave. So what would you do? There are 2 ways to go about it. Simply go from the 0 mark up to 2. That is basically 2. Because you are going up, it's going to be 2 minus 0, which is what? 2. So your amplitude is what? 2 meters. It's as simple as that. It's as simple as I would say it's a maximum upward or downward displacement. Here also, because you are going downward, it's going to be 0 minus 2, being that 0 is higher. So it's going to be what? 0 plus 2, which is what? 2. Still 2 meters. Another way to go about it is this. Take the difference between this point and this point and divide by 2. So that is just this point, 2 minus this point, which is -2 all over 2. What would I give you? This plus 2 minus times minus plus over 2 equals 4 over 2, which is what? 2 meters. So amplitude is 2. Now that is very simple. Let's go to another one. What if you were given a wave that had this, and you were told that this point here is 4 meters, and with this you are now told to find the, let's say you are told to find the wavelength here, the wavelength. So how do you find the wavelength with this? Now it's very simple. Now what you want to do is this. First check how many wavelengths are here. How many wavelengths here? How many circles are here? Let's think of them as cycles. How many cycles do you find here? So we have the first cycle from here to this place. That's one cycle. And then half of the circle. So we have 1.5 of wavelength, right? 1.5 wavelength. So 1.5 wavelength, the entire wave here to this point is 1.5 wavelength. And that is equal to what? 4 meters. I don't know if you understand what I did. I said we're giving this point to be 4 meters, and we are told to check what is the wavelength of this wave. So, and altogether, how many wavelengths do we have? We have 1 wavelength and half, so that's 1.5 wavelengths. So the entire length of this wave is 4 meters, and that entire length is only covering 1.5 wavelengths. So 1.5 wavelengths equals to 4. So it means 3 over 2, 3 lambda over 2 equal to 4. So cross multiply, we have 8 is equal to 3 lambda. And then what do you have? You have lambda will be equal to what? 8 over 3, or 2 number 2 over 3, or 2.667 meters. So you get that. That is how simple it is. All I did was to take how much wavelength do we have here, and take what? So that's. What if you were told, what if this was not in meters? I hope you understood what I did here. We have 1.5 wavelength is equal to 4 meters, and then you do the maths. Is that okay? To find lambda. Lambda will now be equal to 2.66 meters. Now, what if you are told here that this guy, this wavelength is actually, is not now a wavelength of amplitude against time. You know, that was amplitude against wavelength. This is now amplitude against time, and you were told this one was taking 4 seconds, or let's say 6 seconds. So if this wave took 6 seconds, what is the period? Find period. Find the period. So what did we say period is? Period is what? The time taken what? Per revolution. Okay, so you now ask yourself, how many revolutions do we have here? How many circles? Still, we have what? 1.5 circle, right? So 1.5 wavelengths is what we have there. So the entire 1.5 wavelength took what? How much? Took 4 seconds. Took 4 seconds. So how do we find our period? Since period is saying that we should take, period is the time taken per number of revs. What is the total time? The total time is 6 seconds there. Oh, not 4 seconds, sorry, 6 seconds. So 6 seconds over, how many revolutions do we have here? We have 1.5 revolution, which is 1.5, isn't it? So that is equal to 6 over 3 over 2. So this comes up. So we have 6 times 2 over 3. Here 1, here 2. That becomes what? 4 seconds. So it means that it takes 4 seconds per. So to complete 1 revolution, it takes what? 4 seconds. So the period of this wave is going to what? 4 seconds. So what if we were given the speed of this wave, and we are now asked to find, let's say it now says that this wave is traveling 2 meters per second. This wave is traveling 2 meters per second. So it means that each second is traveling about 2 meters. All right. So if it's traveling 2 meters per second, what is the, or maybe centimeter? Okay, let's just use meters, the standard unit. So the wave is traveling, is having a speed of this. So how do we calculate the wavelength? Remember that we said speed is f lambda. You cannot do a lot of derivations here. Is that okay? So for example, let me first solve that question. It says that how do we find for this wave, this same wave, how do we find the lambda, the wavelength? Knowing the speed to be 2 times, what is the frequency? Now we don't know. 2 will be equal to frequency times lambda. And now this is what we're looking for. The lambda, right? The wavelength of this wave. First, we must find the frequency. So what is the frequency? Frequency, we have found the period to be what? 4 seconds. So since the period is 4 seconds, then the frequency will be what? 1 over 4. Isn't it? Because frequency we said was what? 1 over t, if you recall there, the inverse of time. So therefore, period will also be what? From here, you know that since f is inverse of time, then inverse of period, then period should also be what? Inverse of f, if you just work the maths there. So here also, frequency what? Inverse of time. So we have 1 over, what is our period, which is 4? Our period is 4. So it's equal to 1 over 4 is equal to what? 0.25. 1 over 2 is 0.5. Half of that is going to be 0.25. So 0.25 per seconds. So this is our frequency. So what do we have? 2 will now be equal to 0.25 times lambda. So that lambda will be equal to 2 over 0.25. So how do we do this? 1, 2, 1, 2. So we have 200 over 25. Here 1, here 4 times 2, 8. You know in 100, you know it's 100 times 2. So here is 4 times 2 is 8. So lambda is equal to what? 8 meters. So that is the answer. So it means that lambda here is 8 meters. So if I now say, what if the questioner further says, find the distance of this wave, the total horizontal displacement of this wave, total or maximum horizontal displacement. So if you're told to find that, you found out that the wavelength is what? Is 8 meters. And then you now know that the entire distance has 1.5 wavelengths. So if one wavelength, if lambda is equal to 8 meters, therefore 1.5 lambda, if you work the math, that will give you 12 meters. Because it's basically half of this is going to be 4. So 4 plus this. So this place is going to be what? 12 meters. Do you understand? Because that's what the question is asking. The maximum is here. Maximum horizontal displacement for this particular wave. So I hope that is clear to us. So those are the possible questions you can find under this aspect for this progressive wave. The other questions that are going to come up and is going to come up under the next category I'm going to, the next thing I'm going to define, which is the next terminology. And that is the phase. No, let's discuss the wavefront first before we discuss a phase, what a phase is, because I'm going to be rounding it up with this so that the video will not be too long. So, how many minutes? 4. 1 hour. So, let's quickly discuss what a wavefront is. So that will be whatever number we have. A wavefront. Now, what is a wavefront? A wavefront is basically an imaginary line that you draw to connect the points on a wave that are in phase. Okay, so you really need to understand what a phase is. So we're going to talk about a phase now. But, okay, think of okay, good. Let's go to what a phase is. So what is a phase? A phase, if I say 2 points on a particular wave, 2 points on a wave, if I say they are in phase, it means they have the same displacement away from the starting point. The same displacement away from the starting point. That is when we say they are in phase. They are in phase if they have the same displacement away from the starting point. So, for example, this point and this point are in phase. Why? Because they have the same what? They are in the same. They have the same speed, and they have the same displacement away from the starting point. From here to here is the same as from here to here. Is that okay? So they are in phase. Then a wavefront is now an imaginary line that is drawn to join 2 points on a wave that are what? In phase. The most common example, the locus classicus, and that's locus classicus. The locus classicus for this wavefront is, you will see maybe in many of the textbooks, you're going to see that is the ripple tank system. So if I drop a stone in water, what you're going to see is that a wave is going to spread abroad, isn't it? It's going to spread. So, and you're going to see that what this corresponds to is just what? This, isn't it? So all of these points that are in phase here, there's a line that connects them. That line is going to be what? What we call a wavefront. All the points that are in phase with each other. All right. So now, you see, because of the longevity of this video, In the next, I'm going to make a very short video that I will link in this description about questions that are very common with phase and phase difference. So of course, if we say 2 points are in phase, it means they have the same distance away from that horizontal and they have the same speed. What if we now pick 2 points that are not in phase? So we said they are out of phase. 2 points are either 2 points on a wave are either in phase or out of phase. So we are going to talk about the distance between 2 points that are out of phase, and we call it phase difference. Phase difference. So I'm going to link the video in the description. In the next video, we're going to talk about that phase difference, and then in the next video following it, I want to make this one short. Okay. So in the next video following it, I'm going to talk about the characteristics of wave. See you in that next video. If you have not already, please do also subscribe to the channel. It's going to help the channel, and share this video with your friends. And with this video, you have acquired power. Understanding. So understanding is power. Is that okay? So, and with great power comes great responsibility. So you must teach teach it to others. Is that okay? And that's the way to even solidify the information in your own heart. Is that okay? All right. So, and I forgot to tell you, please, you can share this content on many other platforms as possible, please. And God bless you as you do so. See you in the next video. Amen.